All right, ladies and gents, we'll be doing problem 1.11 next. 1.11 says, consider a random process given by x of t is equal to a cosine 2 pi f naught of t plus phi, where a and f naught are constants and phi is a random variable that is uniformly distributed over 0 to 2 pi. If x of t is an ergodic process, the time averages of x of t and the limit as t goes to infinity are equal to the corresponding ensemble averages of x of t. Alrighty, so what in the world are they saying here? So first, what we know, let's just write down what we know first. And that's always a good place to start. So 1.11, we start with the fact that we have a random variable. So a random variable is a variable where the outcome is random. We don't know it. We can't use an equation to say it exactly happens like this. We just know it fluctuates in time or space. We can model it with an equation, but we can't 100% calculate and say this is what it's going to be. So here our random variable happens to be a cosine 2 pi f naught of t plus phi, where the phi is random. So the phase is random. We don't know what the phase is going to be at any given moment. It's a random variable. And we know the phase has a probability distribution function, so it has a PDF, a uniform PDF. So a uniform PDF from 0 to 2 pi. Right, and what they want us to do is they want us to, now read it. I probably didn't read it. So the first part, they want us to use time averaging over an integer number of periods to calculate the approximations to the first and second moments of x of t. So that's part A. So part A, they want us to calculate. Oh, we know the process is ergodic. That's what we need to put. The process is ergodic. And A, for part A, they want us to use time averaging to compute the first and second moments. They want us to compute E of x and E of x squared. And they want us to use ensemble averaging. So they want us to use ensemble averaging to compute the same thing. So they want us to compute the mean, and they want us to compute the second moment. So what does all this mean? Well, first we have to figure out what is ergodic mean. Well, let's start with the PDF actually. This is up here. So we know that x of t's are a cosine with a random phase. We don't know what the phase is. But it tells us what the probability, what's the likelihood of the phase being a certain value in a certain range. So when they say probability, when they have a PDF of 0 to 2 pi, uniform means it's the same everywhere. And it actually happens to be 1 over the range, the actual range. So our range is 0 to 2 pi. So 0 to 2 pi, and you notice it's flat, so it's constant, that means uniform. And the height is actually determined by this. So it's always based, let's say this is B, right? And this is A. Then our probability of choosing a value between B and A is going to be 1 over B minus A. And so in this case, it'd be 1 over 2 pi minus 0, it's just 2 pi. So the likelihood of us having the phase in between 0, choose any value between 0 and 2 pi, likelihood of that being the phase that we get at a random moment in time is 1 over 2 pi. Okay, we got that. Now, what does ergodic mean? Well, ergodic is a fancy way of saying that the outcome of a group of, let's say we're individuals, right, and their lives are random, their events that happen in their lives are random. Well, the average outcome of a group, of all the group's lives are equal to the individual outcome of one person's life in that group. And so it's really a kind of a systems property. And so you have multiple systems and you're tracking the average, what we call the ensemble average. The ensemble, ensemble is usually a group. Ensemble is a word for group. And so you look at the groups, you look at each time or each value at a certain time or specific space in the group. And that, if that is equal to the individual's average at that time or individual's value at that time, then you have what's called an ergodic process. Ergodic in the mean, that is. That means that the ensemble's average, so the outcomes of all the people at a certain time or space, or the average of that, is equal to the average value of an individual outcome. And so I'll just draw a quick example. Let's say you have a trajectory of a ball, right? And it's just, whoop, this is the first process. Let's say it's non-Newtonian, it has a random motion. The motion doesn't follow the traditional laws of physics, right? So then one goes up and then comes back down, and then you have another one. So it's like x1 is x2. These are all systems with random values, right, for their motion. And then you have, let's say you have another one, x4. Let's say this is the ensemble, right? This is the ensemble, and this is the individual. All right, so let's say the individual's motion is whoop, 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 and he comes back and goes that way. I don't know, something crazy like that. So let's say we were to take the average of this person's motion, right? Let's say we computed the average of their motion. So 1 over, let's say x4, and then we'll just say x4 of t, right? So this would be computing their average, right? And then let's say this equals, so let's say this is equal to the average of all of these independently. So the whole, and we add all the independent up together. So we have the whole group. So we have 1 over the summation of all the x's. So x of, it'd be 1, 2, and 3. So we'll just put n here, where n is equal to 1 to 3. And then of course it'd be adding up all of their things as well. So this also would be x of n of t, and then n would be going from 1 to 3. And so you can see here that the average of one person's motion equal the average of the motions of every person in this group. And so that's what a system is ergodic, when it satisfies this condition. And so for a long time I really didn't understand that, but now I kind of see with this example it makes it a lot clearer what they're actually saying here. And so the reason this is important, I guess, another point to point out, the reason this is important is because to compute the first and second moment for a process without time averaging, for example, you have to know its probability distribution function, you have to know its cumulative distribution function, and both of those can sometimes be hard to compute because, for example, this probability distribution function is easy, right, for the phase because, well, they came up with this example and they were able to say that without a doubt. This is a PDF of this. But let's say you have a random signal and it's affected by all different types of noise and complications and things like inter-symbol interference and things of that nature. You don't know what the PDF is unless you can measure it for a long enough time and say, okay, well, it's starting to repeat, so this has in the PDF. You can't really say. So if you say something's ergodic or assume it's ergodic, then you just use time averaging. That's what we're going to do here. So time averaging is a traditional method where you basically find this value of the function over a period or multiple periods, and as the periods start to go out to infinity, it equals the ensemble average. And so let's use time averaging to compute the mean here. And at the end, when we do the ensemble average and the time average, they should equal one another. That means our signal is definitely ergodic and we got it right. Now, the second moment may be different, but we're going to get to that. So let's start with the first part. So first part, use time averaging. Time averaging for m of x, which is going to be e of x, is going to be equal to the limit as or t goes to infinity, 1 over t from minus infinity. All right, we'll do minus. Obviously, it has to be over integer number of periods. I'm going to choose one period because, well, I'm lazy and that's just the easiest way for me to do it. So then you have a cosine of 2 pi ft plus theta dt. All right, so now we're going to compute this. So we're going to do limit as t goes to infinity, 1 over t. This is going to, I'm going to take the antiderivative. So this is going to be, let's factor this a out as well. So let's factor this a out here. This is the antiderivative. This is sine 2 pi f naught of t plus phi divided by 2 pi f naught from minus t over 2 to positive t over 2, right? So then you plug t over 2 in for here, and then you get the limit as t goes to infinity of minus a over t. This is going to, these are going to cancel one another out, so you get a sine of 2 pi f naught of t plus phi over 2 pi f naught minus sine of, so minus sine of minus 2 pi f naught t over 2. This is minus t over 2, right? This should be positive t over 2. And then over 2 pi f naught. Right, so these are going to evaluate to 0 on the inside. So you get limit as t goes to infinity minus a over t times 0. So this part is going to go, this part is going to, anything multiplied by 0 is 0. So this all evaluates to 0. We also could take the derivative if we get it. Anyway, let's just do here, like the limit as t goes to infinity times 0, that's just going to be 0. This is basically the limit as t goes to infinity of 0, which is just 0. Doesn't matter what t goes to, this part is not dependent on t, so it's always going to be 0. So we computed using time averaging that e of x here is going to be equal to 0. Now, we could compute the second moment, and we're going to leave that in a minute using time averaging, but let's go ahead and compute the ensemble average. So we just computed the time average for the mean. Let's compute the ensemble average. And notice, for a process to be ergodic, these have to, the ensemble average has to be equal. So the ensemble average has to be equal to the time average as the limit goes off to infinity, and as we take the time average over an integer number of periods, which is what we did. We did one period, but you get the idea nonetheless. So what we're going to do here is let's go ahead and let's go ahead and compute this. So compute this function here. So the average is going to be equal, the ensemble average is going to be equal from minus infinity to infinity of our function here, which is x times the probability density function dx. We need to change a couple of things here. This is actually dependent on phi here. Phi is our random variable here. And so for the first part, I was writing x of t just as a convention to make it easy, but here our phi is the random variable, and so it needs to be respect to d of phi, and x needs to be respect to d of phi. And so for here, for example, we should have x of it was here times px of, let's do phi, and then d phi. Right, and so then here what we end up having is we have minus infinity to infinity of our function, which is a cosine 2 pi f of t plus phi times 1 over 2 pi. And we can change these bounds as well, because we know that the probability density function is 0 from negative infinity to 0, and then 0 from 2 pi to infinity, positive infinity. And so these bounds go from 0 to 2 pi. Everywhere else the function is 0, so it's going to integrate to 0. But in between here, in between 0 and 2 pi, it's 1 over 2 pi in d phi. And so now we need to calculate this. We can factor this 1 over 2 pi out. It's not dependent on n is a out, so it's going to be a over 2 pi times 0 2 pi of cosine 2 pi f of t v d. Well, we know that. Well, let's just go through and compute this just to see what we come up with. Before I say that, we're going to come through and compute this. So this is going to be cosine 2 pi, it's going to be sine, I'm sorry, it's going to be sine 2 pi plus and nothing divided by it from 2 pi to 0. Okay, so let's think about this. We plug in 2 pi here, right? This is already at 2 pi, so sine of 2 pi is 0. And I need to make a video about that, correcting what I've been doing, but sine of 2 pi is 0, right? So if this t here is an integer, then this will work out. So given that this is going to be 2 pi f naught of t plus a whole nother period, right? So 2 pi is going to be a whole nother period. So this is already at sine of 2 pi, it's going to be 0. So this is going to be 0 with 2 pi. And then 0, when you plug in 0 for phi, you get sine of 2 pi f naught of t. Once again, this is sine of 2 pi f naught t. Given that f and t are integers, then this is going to also evaluate to 0. And so we're left with 0 on the inside, so it comes into 0 times a over 2 pi, which is just 0. So in the end, our ensemble average evaluates to 0. And what we can say then is that the ensemble average equals the mean, the time average. And so because this is true, our process is ergodic. And we confirmed that it was ergodic. It told us that, but we just confirmed it. And so now we can compute the time average of the second moment using time averaging, and then we can calculate the second moment using ensemble averaging. And I won't really go through that here, but if you do want to compute it, which it's not too difficult, if you do want to compute it, right, what you'll need to do is, it's not too difficult. So for time averaging, you're going to do, this is for time averaging, you're going to obviously do from t over 2 to minus t over 2 of x squared of phi d phi, right? And the limit as t goes to infinity of 1 over t. This for time. And for our ensemble, you're going to do e of x. This is going to be x squared, and here's x squared. And then you're going to do minus infinity to positive infinity of x phi minus the mean, so the ensemble, or actually the ensemble average squared d phi. And then times the probability density function, of course. And so you should compute that and compute the ensemble and time average here for this problem. But I really just wanted to show the first part, which was that to show that a process is ergodic in the mean. You also can have ergodicity in the autocorrelation. But here we showed it was ergodic in the mean, and so that we showed the time average was equal to the ensemble average. And that's what we need. That's what is assumed for a lot of communication systems. And so hopefully this video was a little bit informative to you all.